Okay, in this video we will talk about the electric field strength E. An electric field is a region in which an electric charge experiences an electric force. Electric field strength E at a point in an electric field is the electric force per unit positive charge at that point. So you know that from the definition of the electric field strength, E is equal to F over Q. And this is how you get the formula F equal to QE, which you will use later on. An electric field is represented by electric field lines. So for example, let's say now you are given 2 point charges. One is capital Q, another is small q. Find the electric field strength in this position. That means that find the electric field strength in the position same as the position of the point charge small q. And then you know from the Coulomb's law that the force experienced by this charge is this. And then from the definition of the electric field, you can get the expression of the electric field at this point, which is equal to capital Q over 4 pi epsilon 0 r squared. So you notice that the electric field strength at this point actually has no term small q in the expression of the electric field, because the electric field strength here is due to this point charge only, not this point charge itself. So now you only care about the magnitude of the electric field. You only care about the magnitude of the electric field strength. But then, because electric field strength is a vector quantity, that means that E has both magnitude and direction. So we actually care about the direction of electric field also. Okay, so there are now two cases. The first case is that you use a spherical coordinate. Another case is that you use a Cartesian coordinate system. Okay, actually there are also a cylindrical coordinate system, but I don't touch it here. Okay, so we take a look at the case 1 first. If you use a spherical coordinate, you have to remember that the spherical coordinate has 3 important parameters, which is r, theta, and also phi. But then in this case, I want you to focus on r only. R is a radial vector. That means that the radial vector will point from the origin to any other point. That means that from here to here is r, from here to here is also r, from here to here is also r, from here to any other direction is also positive r. Alright, so if I say that positive radial direction, that means that the direction is from the origin to any other point. But then if the radial direction is negative, that means that let's say the electric field points against the radial direction. That means that the electric field strength points towards the origin. Alright. Okay, so now you see, for a positive charge, the electric field is like this. The electric field will point away from the positive charge. So by using this formula, you know that the electric field in the radial direction is this. And then when this is positive, you know that it is along the radial direction. That means that the electric field is coming out of the origin to any other point. Okay, so for the negative charge here, the electric field will point into the negative charge. So from this formula, you know that when Q is negative, that means that ER has a negative value. That means that ER points against the radial direction, and that's why ER has a negative value. Okay, so when you are using the spherical coordinate, you know that the electric field is either along or against the radial direction for a point charge. Okay, AR is the radial unit vector, and then a unit vector is equal to the vector divided by the magnitude. of that vector. Okay, ER equal to negative dV/dr, and then V is electric potential, which I will talk to you in the following video. Okay, in the second case, we use the Cartesian coordinate system. That means that you use x, y, z axis. And then actually I want to say that x, y, z direction can be in any direction you like, but with the condition that x cross y equal to z, positive z. Just now, x cross y equal to positive z, okay? X cross y equal to positive z. As long as you follow that x cross y equal to positive z, the x, y, z direction can be in any direction you like. Okay, so now I use this coordinate system. X is here, y is here, z is here. Okay, so now we take a look at this. The electric field of a positive charge is like this. From this region, the electric field point against the positive x direction, and therefore I say that Ex has a negative value in this region, because in this region the electric field points against the positive x direction. But then in this region, the electric field points along the positive x direction, and that's why Ex has a positive value. Okay, for a negative charge here, the opposite occurs. That means that for this region, the electric field points along the positive x direction. And that's why for here, Ex has a positive value. But then for this region, the electric field points against the positive x direction. And that's why Ex has a negative value. So in the Cartesian coordinate system, you can consider in x-axis or y-axis or z-axis. So let's take a look at the y-axis. So for this region, the electric field points along the positive y direction, and that's why for this region, Ey has a positive value. But then for this region, electric field points against the positive y direction. Therefore, Ey has a negative value in this region. Okay, then you know that the opposite occurs here. Okay, because you have to remember that for a positive point charge, the electric field is coming out of that positive point charge. But for a negative point charge, the electric field will point towards the negative point charge. So just now you already learned that if the electric force is positive, then it's a repulsive force. If the force has a negative value, then it's an attractive force. But then for the electric field strength here, you really have to take a look at the direction, because the direction means a lot. For example, if I only take the spherical coordinate system, from this expression, I know that the electric field is either along the radial direction or against the radial direction. And then for the gravitational field strength, there is always a negative sign in the electric field, the gravitational field. So you know that the gravitational field will always point towards the mass. Okay? The gravitational field will never point out of the mass. Okay? So an electric field is represented by electric field lines, and then the electric field strength is visualized, is indicated, is represented by the density of electric field lines in that region. That means that how many electric field lines in one region. For example, let's say you do a small circle here. You know that inside the circle there's 1, 2, 3, 4. There's 4 lines passing through this circle, so that you know that, wow, the electric field here is quite strong. Now you do another circle here. Only one electric field line is passing through this circle. So you know that the electric field strength here is much stronger than here. Okay, because at least here I can have 4 lines. here I only have one line, so you know that the electric field here is stronger. Okay, and then for example here, there's totally no electric field line in this point S at all. Therefore, actually the electric field strength at this point is 0. Because electric field strength from this point charge is to here, and then the electric field strength from this point charge is to here, so they cancel out. So the electric field strength at this point here is 0. But then the electric field strength here is not 0 because they actually add them up. Because the electric field from this positive point charge is to this direction, but the electric field from this negative point charge is also this direction, so they add up instead of cancel out. Okay, so and then you have to notice that the lines, the electric field lines, never cross each other. They never overlap. Okay, that means that you can never draw the lines to be overlapping. It's definitely wrong. The lines will surely not cross each other. Okay, so based on the 4 points chosen, P, Q, R, S, please arrange the electric field strength in descending order. That means that I want you to arrange the electric field strength from the strongest electric field strength all the way to the weakest electric field strength. Okay, so you know that the electric field strength at P is larger than Q. Why? Because P is nearer to this point charge than Q. And then you really have to know that normally the electric field in between this dipole, okay, for the two equal charges but opposite sign, we call it a dipole. And then normally in between the dipole, the electric field strength is greater than outside the dipole. Because the electric field strength in between the dipoles will be contributed by both the charges because they are all in the same direction. But then for this region, the electric field from the positive point charge is to this direction, and the electric field due to this negative charge is this direction, so they actually cancel out each other. Okay, so definitely the electric field strength in between the dipoles should be greater than the electric field strength away from the dipoles. Okay, and then you know that definitely the electric field at this point S is 0 because they straight away cancel out each other when the point S is equally distant from here and from here. Alright. Please notice how the electric field lines curve, because this is wrong, this is correct. This is a dipole. And then when the electric field lines is further away from the negative point charge, it will be more influenced by the positive charge here. That's why it will curve this way. When the electric field line is very close to the negative charge here, it will be less affected by the positive charge here. Then that's why the line here is almost like a straight line. Okay, so this is wrong. This is correct. It should curve this way, not this way. And then you can also view the electric field as a superposition. That means that the electric field from the positive point charge is this direction. The electric field from the negative charge here is this direction. So you know the resultant electric field is this way, and then that's why it's tangential to the line here. You can also view that at any point you like. For example, okay, let's choose this line. The electric field due to the positive charge is at this direction, and the electric field due to the negative charge is this direction. And that's why when you do a parallelogram, it will have a direction here. Okay, this is the resultant electric field. This is the electric field due to the positive charge, and then this is the electric field due to the negative charge. Okay, of course this is a parallelogram. I know that I didn't draw it very well. Okay, this is a parallelogram. Okay, and then this is certainly wrong because what is correct is like this. Okay, you have to really care about how the electric field lines curve. This is curved this way, this is curved this way. Alright, So let's do some questions. Electric field intensity, which is also electric field strength, at a point is 3 times 10 power 3 Newton per coulomb directed to right. Find the direction and magnitude of the force acting on the positive 17 nano charge at that point. Okay, I need to tell you that the electric field will point from the region of higher electric potential to the region of lower electric potential, and then the positive charge will tend to move towards the region of lower electric potential. And then from the definition of the electric field, E equal to F over Q, you can get this formula. Alright, and then please find the force acting on the negative 5 nanocoulomb at that point. Okay, just now I mentioned that the positive charge will move to regions of lower electric potential. Now the negative point charge will move towards the region of higher electric potential. Okay, so you can find the force and also the direction. Please find the electric field at point X due to Q1 and also Q2. Remember, the electric field points out of the positive charge and points towards the negative charge. And then you can use your powerful geometry to find the resultant electric field. Okay? And then also you have to give me a diagram, give me an angle, and then you find that angle for me so that I know the resultant electric field strength and also the direction of the resultant electric field at point X. So now 4 charges are located at 4 verticals of a square of dimension A respectively. Find the electric field strength at point P, which is at the center of the square. Okay, this is positive charge. So you know that the electric field at this point due to this is in this direction. And then the electric field due to this negative charge is also in this direction. The electric field due to this positive charge is this direction. And then the electric field due to this negative charge is also this direction. Okay, so you know that E due to Q1 is there, is here, is to here. And then what is the distance between the point P and the positive Q here? You have to use your geometry. That means that D is the diagonal of the square. This is D. D square equal to A square plus A square. And then D equal to 2R. Okay, 1R, 2R, 1D. So ultimately you can find the value of the R. Okay, then you substitute the value of the R. Because remember, R is the distance from the point from the point charges. Okay, and then the electric field due to Q1 is exactly the same as the electric field due to negative Q here. So you know that they straight away times 2 because they add up each other. The same happens for the electric field due to Q2 and Q3. They are in this direction. So you know that when there are 2 electric fields here, the resultant electric field is here, because you do a parallelogram and then you can find that it is vertically downwards. How do you know that it is 45 degree and 45 degree? Because this is a square, so I know that the angle here is a 90 degree, and then 90 degree divided by 2 equal to 45 degrees. Okay, so you know that the net resultant electric field is equal to this electric field cos 45 degree plus this electric field cos 45 degree. Okay, so now there are 2 point charges, and please find the location of a point where the electric field strength is 0. When the electric field strength at a certain point, let's say this point, okay, is 0, then you say that the summation of the electric field is equal to 0. Alright, but then remember, because the electric field from this point charge is to this direction, and then the electric field from this point charge is to this direction. Alright, so although you should say that E1 equal to negative E2, But then I really just care about their magnitude, and that's why I put the modulus. Okay, that means that I want to find E1 equal to E2 because I really know the direction of the electric field are opposite. Okay, and then try your best to find the x. Okay, that means that x is a unknown distance from Q1. Okay, so that you know that at this position the net electric field is 0 because they already cancel out each other. Okay, so now two oppositely charged particles of equal magnitude, which is a dipole, are placed at an equal distance d from the origin. Which graph represents the variation of magnitude of electric field E along the x-axis? So now we are not sure whether the electric field is using the spherical coordinate system or the Cartesian coordinate system. But then let's do it from the point of view of the Cartesian coordinate system first. That means that we only look at the electric field along the x direction first. Okay, for this region, the electric field is pointing to the negative x direction, so it should have a negative value. In this region, the electric field points towards the positive x direction, so it has a positive value. In this region, the electric field points towards the negative x direction, so it should have a negative value. And then we also remember that in between the dipoles, that means that in between any point here, the electric field strength due to this positive point charge is to this direction, and then the electric field strength due to this negative point charge is also along this direction, so they add up each other. But then outside the region from the dipoles, that means that in this region and also in this region, the electric field due to this positive point charge is to here, but the electric field strength due to this negative charge is here, so they cancel out each other. So you know that the magnitude of the electric field in between the dipole is much greater than the magnitude of the electric field strength outside the dipole. So you know that the height of this is definitely much larger than this height. Okay, this is much larger than this. But now let's take a look at the options. In all the options, the electric field strength only has positive value. So what do? You just simply take the modulus of this graph. That means that every positive value stays positive, but every negative value becomes positive, and therefore you know that the answer is A. That means that they really don't care about the direction anymore. They only care about the magnitude, and that's why it has no negative value whatever. So in the following video, we'll be talking about the electric flux, which is about the Gauss law. Thank you.